Hey guys, welcome back to chapter number 6. This is the last lecture that we'll be doing for the second exam. We'll do remembers chapters 4, 5, and 6 on this exam. And so we're going to start talking about gases. So we're going to leave solutions, we're going to leave aqueous, the aqueous realm, if you will, the liquid realm, and we're going to go look at gases, right? And just a few things about gases. We'll look at some simple gas laws. We'll look at the ideal gas law in this video. And then in the next video, we'll look at ways that we can manipulate the ideal gas law to calculate or to look at a variety of different problems. And so the first thing we want to talk about, though, are gas molecules, right? Gas molecules themselves are constantly moving. Unless we talked about going to absolute zero, that those gas molecules may be slowed down a little bit, almost stopping, but they're constantly moving. And so what we see with gases is we see this thing called pressure, right? And the pressure is the force exerted by or per unit area by gas particles as they strike the surfaces, right? So as the gas particles are moving, they're going to come in constant contact with everything they're hitting, including the walls, including at the inner ear. If you've ever been on an airplane, and this is why as you increase in the altitude, your ears need to pop, is because the pressure on the inside of your ear stays the same. It doesn't change, but it's that pressure on the outside of your ear. And usually when we're on the ground, when we're where we usually live, those pressures are equilibrated. But so then if we go to a place that is very, very low pressure, that becomes out of equilibrium, and so then it needs to pop. And so pressure comes from, the molecular collisions. As we said, it's the force divided by the area. And, because there's a number of gas particles in a given volume, the more the increase altitude, usually the decrease in the pressure. And so we measure pressure in a variety of different ways. One of the ways that we measure pressure is the most common way is through millimeters mercury, and we'll talk about a barometer, what that looks like. Really just a barometer is a bowl with mercury in it. An old school barometer is a bowl with mercury in it, and there's a tube with gradations, and they would see the pressure and they would be able to measure it based on how high or low it was. You might hear barometric pressure. That's where it comes from. And so it's millimeters mercury. Now, millimeters mercury is the same as a different pressure unit called torr, T-O-R-R. So on an exam, if you see torr, it is the same as a millimeter mercury. We can use things called atmospheres, ATMs, and that's one we're going to be using for these gas laws. When we talk about pressure of these gas laws, this is the average pressure at sea level, and that 1 atmosphere is equal to 760 millimeters mercury. We know that there's also a Pascal. This is the SI unit of pressure, whereas 1 Pascal is equal to 1 Newton divided by meter squared. We're not going to talk about we're not really going to use pascals. In this class, you might be asked to convert it on a homework assignment. Maybe that's on there just so that you can practice converting units. You'll get a table. You'll know the conversion units. You'll convert it the same way. Pascal is much smaller than an atmosphere, right? 1 atmosphere is equal to 101,325 pascals, right? So this is a very minute unit of pressure. We're familiar with, we are familiar with pounds per square inch. If you're filling up your tire, you notice your tire is low, you put the little reader on it to see how flat it is, and it reads in PSI, right? Per square inch, pounds per square inch. 1 atmosphere is equal to 14.7 pounds per square inch. And this is a table here where we're looking at the common units of pressure. Again, if you were asked to convert one, like let's say you were asked to convert pascals to atmosphere, I will give you guys that conversion. One conversion I will probably give to you. I don't want to say never, because I haven't looked at the exam yet and what I've given in previous years. I will probably give you the atmosphere to the millimeter mercury conversion unit, but we're going to be using that so much that you'll probably memorize that 1 atmosphere is equal to 760 millimeters mercury or 760 torr, right? And that is an exact conversion. And so we talk about pressure and we talk about different areas of pressure. If you ever try to bake a cake here in Texas, and then you try to bake a cake in Colorado, when you get higher up into the mountains at a higher elevation, they're different. And if you look at the back of a cake box, it'll usually change the recipe slightly for those higher altitudes because the pressure is different. Water boils differently at different pressures, right? That's why when you guys did your thermometer correction in lab, we had to know the atmospheric pressure because it slightly changes the temperature of water boiling. And so then how can we measure the pressure of a gas, let's say, versus the atmospheric pressure? And so we can use something known as a manometer. A manometer can help determine the pressure exerted by a sample of gas. Looking at, again, millimeters, usually mercury. Now, I will warn you, on an exam, on my exam, I will not put a manometer question on there. Or at least I will not put, okay, you have the mercury, you see it decreases by 5 millimeters. What is the pressure of the gas, right? I'm not gonna do that specifically. We will have to know, though, conceptually what a manometer tells us. That we will need to know, but maybe on your final or even on your homework, a specific question about a manometer will be on there. I put it on your homework for the sole purpose that it might be, not will be, but it might be on your final, the specifics. And so we just want to be exposed to it, if you will, before we get there. And so what can we do with this manometer? So what you can see is there's an open end to your left that's open to the atmosphere, right? And so the atmospheric pressure is pushing against that mercury. And then what we can do is put a little bulb on the end with our gas in it, and we can hook that to the other end. And so then that is going to push on the other end. And there's a little J, a little kink in the tube. Now, the height difference between the atmospheric pressure and our pressure will determine what is at a higher pressure. And so if you see like what's depicted in this picture, where it goes up higher towards the atmosphere versus the high pressure gas, then that means what would that mean? If we were to see this, we do this experiment and we see this J tube and the mercury rises towards the atmospheric side, which gas, atmosphere or our sample, would have a higher pressure? That's right, our gas sample would have a higher pressure. Now let's say we see the opposite, right? To where instead of it looking like this, we just flip it around to where the mercury is rising towards our sample and decreasing towards the atmospheric pressure. That's right. It is meaning that the atmosphere is at a higher pressure than our sample. But what if they were equal, right? What would happen if the mercury were to equilibrate in the middle and you wouldn't actually see one higher or lower? That's exactly right. The pressure of our gas is equal to the atmospheric pressure. And that's a concept that I really want you guys to know about this, is just what we can tell by how the mercury moves, whether our sample is of a higher or lower pressure than the atmosphere. If you have any questions, just please ask me, and I'll be sure to try to answer them. So what are some basic properties of a gas that we're going to really study and that we're going to look at? And we're going to look at some relationships, some simple relationships. We're going to just briefly introduce them through the slides, and then we'll go to the board and we'll look at these in a little bit more detail and why we can, and talk about the relationships that we do. Well, the 4 basic properties of a gas are pressure, volume, the temperature, and the moles or amount of the gas molecules that we have. Each property, as we'll see, is interrelated to each other. So if you change the pressure, you'll change the volume. If you change the temperature, you'll change the pressure, and vice versa. And because of this, we can check and we can test and we can see some of these basic relationships, and we can put them into what's known as some simple gas laws. Simple gas laws are simple because we're only looking at 2 of the 4 basic properties of these gases. So what's the first gas law? And we will have to know what the gas laws, what these simple gas laws are. The first gas law is Boyle's law, right? Boyle's law details the relationship between volume and pressure, right? And he used the J tube, just like what we saw with a manometer, to test this out. But what he sees, and what we're going to talk about again when we talk about the board. So I'm just using words here. We'll go a couple slides, and then we'll look at it on the board, and then we'll see how we can relate all of these together. But what Boyle saw was that volume is inversely proportional to the pressure. And so what that means is the bigger the volume, the lower the pressure, right? So the higher number for the volume, the lower number for the pressure. So that if we were to decrease the volume, we would increase the pressure. So like what we see on the picture there, if we had a volume of 1 liter and let's say the pressure was 1 atmosphere, if we were to decrease the volume by half, our pressure would increase by 2. That's what we mean by an inverse relationship, an inverse proportionality of these two units. So then what did Charles describe? So Charles described, we'll go ahead and get the little picture there. So what Charles described is that there's a relationship between volume and temperature. And this is a direct relationship. Now he figured it out by ascending by a hydrogen-filled balloon, right? The precursor to our hot air balloons. And he did it to ascend. If you want to, there's a very good Amazon movie about meteorology and how we found out weather and ways things work that actually illustrate this. And of course, I'm going to say it and I forget the name of the movie, but it's about hot air balloons. And it's a really good one. And it's very similar to what Charles did. But we've seen this in real life, right? We've seen this in real life. If you've ever had a balloon at a birthday party and you put it in a very highly air-conditioned room, the balloon tends to shrink. Whereas if you were to take a balloon into your heated car on a hot Texas afternoon, it will expand, right? And because we have to think about, why is this the case, right? Again, think about, why is this the case? So let's go back to this. Why would a smaller volume lead to an increase in pressure? That's exactly right, because pressure is how many times a gas molecule hits against the surface. So if there is less area for them to move, they're going to hit more often, increasing the pressure. Why would temperature be proportional to the volume, right? Why would a lower temperature lead to a smaller volume and a higher temperature lead to a bigger volume? That's exactly right, because temperature is the kinetic movement of molecules, right? The warmer something is, the faster molecules move. The faster they move, what's going to increase? We're not going to talk about this one. The book doesn't talk about this simple gas law, but we will talk about it. I'll add to it that pressure is directly proportional to temperature, right? The higher the temperature, the faster these molecules are going to be moving, the more the volume is going to be expanding. And the vice versa is true. The colder it is, the smaller that they're going to get. So then what is Avogadro? Man, we're coming back to Avogadro. Avogadro says that volume is directly proportional to the amount, the moles of the gas, right? So obviously the more gas you have as you blow up a balloon, right, the bigger the balloon is going to get because you have more gas. And so let's go ahead to the board real quick. And so what we're going to do is we are going to go ahead and we're going to look at these relationships. And then what we're going to look at, and you will not have to derive the ideal gas law. On an exam, you will never, because we're not a math class, you will never have to derive any of these laws or any of these, whatever we're going to talk about. But you will have to, I think we should know how it happens because it helps us maybe expand our mind and maybe know why we get it. So let's look at Boyle's. So we're going to do this relationship for boils. Now, what did we say about boils? Right, we said that the volume is inversely proportional to the pressure. This little symbol here, I don't know if you can see it. It looks like a sideways A. Yeah, you can see it. It looks like a sideways A or like a something like that, like an alpha. That means proportional to. So volume is proportional to the inverse of pressure, right? As we decrease the volume, we're going to increase the pressure. As we increase the volume, we're going to decrease the pressure. What we can do is take this thing out and make an equal sign of it by multiplying this by some constant, right? So this proportional to, we can change it to an equation by multiplying by some constant. Now, let's say we look at, let's go ahead and solve then for this constant, and you'll see why. So we're going to multiply both sides by P. So PV equals some constant. Now, you know what's really nice about constants is they never change. And so let's say we're looking at gas number 1. And let's say we change the pressure of gas number 1 to make a new form, right? The gas is a new treatment. Well, you know what's going to happen? So is the volume is going to change. And what we can actually do is, since the constants don't change, we drop it out. And so we made P1V1 equals to P2V2. Where did we see something very similar to this? Exactly, with concentration. We had M1V1 is equal to M2V2. It's all coming together now, right? So let's look in a very similar fashion to the other gas laws that we have. And what we're going to do is we're going to look, so this was boils. I'm going to leave boils down here, but what I'm going to do is I'm going to erase these, because we're going to look at a different one, and we'll solve it, and then I'll give you the last one just as a way that we can see it in the equation form. Charles, that volume, right, we said was directly proportional to temperature. Temperature goes down, volume goes down. Temperature goes up, volume goes up. So then what we know is volume is equal to some constant. And what we're going to see is we're going to solve it the exact same way, right? So volume divided by temperature is equal to some constant, right? And so let's say we have gas number 1. Whoops, got ahead of myself. Right, that the volume of a second gas divided by the temperature of the second gas is going to be a constant. And so if this is Boyle's, this is Charles's. So the volume now, that's Charles's law. I would make a comment about Charles is in charge, but it seems to me that that is an outdated reference to an old TV show that nobody watches before, and that's okay. So there's Boyle's law, there's Charles's law. The units for these problems, it doesn't matter, just like the M1V1 equals M2V2, as long as they're all the same and we know what they are, we can just plug in and solve. So then we talked about, the last one we talked about was Avogadro's. I'm just going to put AVO. And that is the volume, right? Because they're directly proportional to, just like Charles's law, it's going to be volume of 1 divided by the moles of that gas. And then let's say we add more, so we have an N of 2. Then we know we're going to have a new volume. And so let's go ahead, and I'm going to give you another one. There's another guy named Gay-Lussac. And what he saw was that pressure and temperature were directly related. And right? So the higher the temperature, the higher the pressure. You see this, I saw this especially in Indiana, when you'd go out and it was minus 6 degrees outside and your tire was flat, right? The pressure of the gas decreased and because of the temperature. And so here are just in equation form, the basic relationships between 2 of the 4 properties of a gas. Now there are assumptions that we are making. And I want you guys, I'm going to tell you the assumption, let's say we make in Boyle's law, and I want you to tell me and think about, we're not going to cover it, but I want you to write it in your notes, the assumptions we make for these other 3, right? So for Boyle's law, where we see pressure and volume, we are assuming that the moles of the gas stay the same and that the temperature doesn't stay the same, right? Because we're only looking at pressure and volume. So temperature has to stay the same and the amount of gas has to stay the same. Because if it doesn't, then we would have to do something else. And so I want to leave you guys with this because of the timing. And then what we'll do is we'll start here next in part 2, and we'll see how far we can get. So we had Boyle's law, right? We have Charles's law, so this is B, C. We have volume, temperature, and then we have Avogadro's law. I won't put in Gay-Lussac's law, but if you wanted to, you could actually solve it from what we're about to do. Now let's combine, because what do all of these have in common? That's right, they all have a volume on this side. So volume is proportional to temperature, the number of moles, divided by pressure, right? So all we're doing is just combining all of these. Now, what do we say about this thing? We can turn it into an equation by multiplying it by some constant. In this case, I'm going to call that constant the letter R. And then we have T(n) over P. Now, I don't like having, a divisor over here. So I'm going to multiply both sides by P. And what I get in the end is PV equals, I'm going to rearrange these, right? Because then we're multiplying R, T, and N. So it doesn't matter which order we're going to put them in. But I want to put them in N, R, T. And so what has happened is we have now combined all of our simple gas laws and the simple relationships that we see with gases into what's known as the ideal gas law. And so here it is, the ideal gas law. And so if you were to ever forget one of the simple relationships, we just have to remember the assumptions, and we can use the ideal gas law to show us those simple relationships. Okay, and so we're going to pick up we're going to pick up the next part of this chapter here, and then we'll look at maybe a few math problems, and then how we can use the ideal gas law to calculate molecular weight, and then we'll talk about real gases and how they maybe deviate from the ideal gas law.